Hi everyone, I welcome you to the presentation of this lecture, Automatic Control Systems, topic called Mechanical Translational Systems. So we're going to discuss two domains. There is a time domain and the frequency domain. This lecture, my interest in the time domain, so I'm just discussing the time domain. So under this, we're going to be looking at three parameters. We shall be discussing a mass, a dashpot, as well as a spring. So we're going to have two conditions. We will have a condition which we're calling a fixed condition. Under fixed condition, for a mass, it will look like this. You have a mass with a pushing force, of course, and it will be fixed at the reference point. The displacement it's taking will be represented by x of t. For a dashpot, it will have a force. A dashpot looks like this, and the reference point, which is showing that this thing is fixed, and the displacement is there. So for a mass, we'll be using m. For a dashpot, we'll be using b. And then for a spring, it's the same arrangement. Force, the spring, and the reference point. For a spring, the constant will be using a k, and this is the displacement, the movement of a spring. So these conditions are for the fixed. And then we're going to have the unfixed condition. But before we come to the unfixed condition, these are the equations we have. So for a mass, the force is given by, because we know that mass is directly proportional to acceleration. So mass is equal to, force is equal to mass times acceleration. So mass times acceleration in terms of displacement, we are just differentiating the displacement twice. So it's d2xt dt squared. So this is the representation of mass times acceleration in terms of displacement. Then for a dashpot, we know that force is given by the constant on the dashpot times velocity. So for a mass is the constant, which is a mass, times its acceleration, which is that one. For a dashpot, it is the constant, which is the b, times the velocity. Velocity there, it's the differential of the displacement, which is this one. And then for a spring, it is the constant times the displacement. So the constant for a spring is k, the displacement is x of t. So these are the three equations. For mass, we'll be using this. For a dashpot, we'll be using that. For a spring, we'll be using that. These are both fixed. Now, when we go to the unfixed conditions, or the conditions which are not fixed, we're going to have these parameters. The same things, but you realize that this reference which was there is no longer there. So if it's not there, we're going to be having two displacement. Like for a dashpot, you have a displacement as the initial as well as the final. Even for a spring, the initial displacement and the final. For a force, it's not every time that you'll be having forces. You'll see as questions come. But for a mass is only affected by one displacement. So the equation stands for mass. Force will still be the same, either for fixed or unfixed conditions. But for the dashpot and the spring, things will change. For the dashpot, you see that it's exactly that, except since you've got two displacement, this one and that one, so it will be the differential, of course, but the difference between the two, the initial minus the final. Or this one, the starting one minus the one which you're in, so you're going to have that, the difference in those. Okay, same applies there. You have this one and that one, so just subtract the two, then that will give you the final displacement. And you're having that force is equal to k times, instead of x of t, since you've got two x of t's, so you are finding the difference in the two. Let's look at an example. So I got this example in one of the TVETA exams. The question reads, the mass spring system is shown below. Derive the expression for the displacement in the time domain. So as you can see, we've been given a force there acting on this mass, and there's a displacement there, x of t, with a spring attached there, and then it's fixed there. So in our solutions, what we are supposed to analyze, we always analyze equations on masses. So the number of masses in a system will tell you the number of equations you're going to have. So this system has one mass, therefore it will just have one equation. So we're going to analyze for the mass. We know that for the mass, the equation we are having is this one, force. On this mass, there is a force. It's m d2xt over dt squared. So this is the equation for the mass. And then for the spring, it's just k, the constant k times the displacement. So it's going to give us that equation. Therefore, the whole system now is a combination of those. If you combine those, you're going to have that. This is the equation for the mass, and this is the equation for the spring. So we are having this as the equation now, example 1. The next slide, let's look at example 2. Okay, on example number 2, the question reads, the mass, spring, and dashboard system is shown below. Derive the expression for the displacement in the time domain. So as we can see from this question, we've got a reference. Attached to it is a spring K1 of constant and dashboard constant B. There's an external force F of T, and there is a mass there M1 with a displacement Y1 of T. And another spring is attached between M1 and M2 with a constant K2, and there is a displacement on M2 which is Y2 of T. Okay, so since we've got two masses, we're supposed to have two equations. The number of masses is equivalent or is proportional to the number of equations you're supposed to have. So two masses means two equations. So let's start analyzing at mass 1, where we're going to have equation number 1. At mass 1, we realize that the system will look like that. Okay, so this is what we will have at mass 1. So with that, our analysis, you realize that we're supposed to form an equation f of t with parameters on m1, k2, k1 as well as b. So when we do our analysis, we realize that we have that f of t is basically equal to, for the mass, it is mass times acceleration. The acceleration we know is the differential of the displacement twice, which is that one d2yt over dt squared. Then b is the velocity. Velocity is basically the differential of the displacement. So it is b times, we are differentiating the displacement. That's what we are having there. And for k1 there, since k1 is fixed, so it only have one reference there, one displacement there. That's why I'm saying k1 times that one. But when we come to k2, k2 is not fixed. It's sitting between two masses, m1 and m2, and there are two displacements there. Therefore, you subtract y2 from y1. Why are you subtracting y2? It's because we are at m1. So it will be y1 minus y2. So this is the equation we are going to have according to our analysis at mass 1. Then, if we analyze at mass 2, we realize that your system will look like this now. So your system will look like that, where you're going to have the mass M2, then we are having K2, the spring, and the displacement, of course, there, which is that one there, Y2 of T. So with that, of course, we know that we are supposed to have the external force F of T giving us those equations. So M2 is equal to the differential, because this is acceleration, so that's the equation you have there. And then K2 is supposed to be the difference between the two. So which one do you subtract? Now this time around you're subtracting y1 from y2. Why? Because we are analyzing at m2. So we are at m2, supposed to be y2, then you subtract the other displacement, which is y1. You're going to have that. But as you can see from the system there, we don't have an external force. Therefore, the external force there, F of t, is 0. Then the equation reduces to that. Okay, so these are the two equations you're going to have, this one as well as that one. Thanks for watching.